So far we have seen that Fermat's little theorem is a way to almost separate primes from composites, and we're using that as the basis of our test to see if a number is prime. So if it passes this test, our number is acting like a prime. We've seen that the problem is that there are certain numbers, Carmichael numbers, that pass the test even though they are not primes, right? So it's not a perfect test yet. So in order to improve what we have so far, we're going to bring in another property that somewhat separates primes and composites. And here it is. It says that if you have a number that is congruent to 1 when you mod by n, and you take that number's square root, if that square root is not 1 or n minus 1 when you mod by n, then n has to be composite. N has to be composite if that is the case. So put another way, if your n is prime and you have an a that is 1 mod n, then the square root of a has to be 1 or n minus 1. It's kind of the contrapositive way of saying it. So we need to look at an example to see how this all works. So let's look at n equals 8. We know that's a composite, right? So let's look at some numbers that we will be able to take square roots of. 1, 4, 9, 16, 25, 36, 49, and I'll stop there. So do any of these satisfy the hypothesis of being 1 mod 8? Well, 1 is obviously 1 mod 8. 4 is not. 4 is 4. 9 is 1 mod 8. 16, that's actually 0 mod 8, so no. 25 is 1 mod 8. Right? 8 goes into 24, so a remainder of 1. 36, no, that's 4 mod 8. And 49, yeah, that's 1 mod 8. So we actually have 4 values for a that fall into this category of being 1 mod 8. So now let's take the square roots. Square root of 1 is 1, square root of 9 is 3, square root of 25 is 5, and square root of 49 is 7. So if now we mod 8 all these guys, but these guys are all less than 8 already, so 8 goes into all of these 0 times with themselves as a remainder. So 1 is 1 mod 8, 3 is 3, 5 is 5, and 7 is 7. That part was easy. Alright, so what the theorem, this fact, says that the square root of a, if it's not 1 or n minus 1, so for us that would be 1 or 7, then n is composite. Well, this one is 1, so that was okay. This one is 7, but these are not, right? So we had a number that was 1 mod 8, and when we took the square root, it was not 1 or 7 mod 8. And same with this one. 25 was 1 mod 8. When we took the square root, it was not 1 or 7 mod 8. So this says that it must be composite. And of course, 8 is composite. Okay, so that's an illustration of how this works. Now let's do a known prime, 7. And again, let's look at numbers that we can take the square root of. So 1, 4, 9, 16, 25, 36, and I'll stop there. So when we mod by 7, we get 1 mod 7. 4 is 4 mod 7. 9 is 2 mod 7. 16 is 2 mod 7. 25 is 4 mod 7, right? 21, okay. And 36 is 1 mod 7. So 2 of them are 1 mod 7. So they're the ones that the theorem might apply to. So we take the square root of those 2. we get the square root of 1 is 1, square root of 36 is 6. Now, of course, when we mod those by 7, we get 1 and 6. And again, the fact says that the square root, if it's not 1 or n minus 1, so that would be 6 here, 1 or 6, then it's composite if any of them are if any of them are not 1 or 6. But we got a 1 and we got a 6. So they both passed. Okay. So that means we can't say that 7 is composite. It does not mean that 7 is definitely prime, I should say. This, unfortunately, like Fermat's little theorem, doesn't say that if it always is 1 or n minus 1, then n is definitely prime. So again, there could be some composites that sort of act like a prime with respect to this fact. But anyway, we know 7, of course, is a prime, and it is working, right? So that's an interesting property that primes, well, I guess that composites have, I don't know how you want to say it. Composites sort of fail the quote-unquote test because they have these square roots that aren't what they're supposed to be. Primes always give you a 1 or an n minus 1 when you take the square root. Okay. I want to just show, this is actually not super hard to see why this is true. So I didn't show you why Fermat's little theorem is true. I just showed you a preponderance of evidence. Rather than showing you a lot more examples to get you to believe it, I've shown you 2 examples, but I actually want to just show you directly why this has to be true. So it goes like this. Suppose we have a number who is 1 mod n. All right, and again, we want to look at the square root and what it is mod n. But one thing I could do is I'm going to subtract 1 from both sides. So a minus 1 then would be 0 mod n, right? Which means if you're 0 mod n, it means n goes into you evenly, right? Because the remainder would be 0. So n divides a minus 1 evenly. Okay, fair enough. Now, a minus 1, I'm actually going to factor that. I'm going to factor that because we're assuming a is, we can take the square root, right? So a is a number squared. So this is the difference of 2 squares, and back in algebra class we remember how to factor difference of squares. So it's the square root of a minus 1 square root of a plus 1. So n divides that evenly. Okay. Now here's where whether or not n is a prime matters. So if n is a prime, that would mean since n divides these 2 guys multiplied together, n would have to divide either this one on its own or this one on its own. Or maybe both, but it has to be at least one of them. Right? I mean, think of prime factorization. This guy has its prime factorization. This guy has its prime factorization. If n is prime, then it's got to show up in either one of these guys' factorizations. See, if n is composite, like say 8, right? We were dealing with 8. Then see, 8 could divide into this whole thing without dividing into one or the other, because maybe this guy is divisible by 4 and this guy is divisible by 2, and so when you multiply them together, it's divisible by 8. But neither of them individually would necessarily be divisible by 8. But that's because 8 is 4 times 2, right? So if you have a prime like 7, you can't do that little trick. So if this is divisible by 7, then either this is divisible by 7 or this is divisible by 7, or maybe they both are, but like I said, at least one of them is divisible by 7. That is the difference between that's the difference between prime and composite right there. Okay, so now if n is prime, then we can separate this. N divides this or this. So let me just go backwards and say, okay, well then that means square root of a minus 1 is congruent to 0 mod n, or square root of a plus 1 is congruent to 0 mod n. Now here I'm going to add 1 back to both sides, so square root of a would be congruent to 1 mod n. Okay. Now this one, if I could subtract 1, but we get into negative numbers. What might be easier, that would be fine, but what might be easier in terms of me explaining this is, instead of putting a 0 here, let me replace it with n, right? Because n and 0 are the same mod n, right? N is 0 mod n. N goes into n one time with a remainder of 0. Just like n goes into 0 0 times with a remainder of 0. They both have a remainder of 0, so they're both the same mod n. And that'll just avoid getting into negative numbers. So now I can subtract 1 from both sides. All right. And so now I see that if I started with a number that was 1 mod n, and n is prime, then the square root has to be either 1 or n minus 1 mod n. Has to be. So therefore, just switch that around. Therefore, if when we take the square root of a, it is neither 1 nor n minus 1 when we mod by n, it couldn't have been prime. So it must be composite. And that's what our property says. Okay, so going forward, we'll now try to fold this fact into our existing Carmichael test for primality.